Hey everybody, welcome back for Chapter 2, Part 2 for the metric system. Hopefully you have watched Part 1. That's where we go over the metric system, how to use the prefixes, and how to do conversions. In this second part, we're still going to talk about some conversions, but we're also going to talk about volume, density, and some other topics. Let's start with volume. You may remember calculating volume in high school. Length times width times height. You might also see length times width times thickness, so that's what the T is. I won't bore you with doing a practice calculation of that, but I do want to remind you that all three of those measurements, the length, the width, and the thickness or the height, must be in the same units. For example, if you have your volume, if you need to calculate your volume and you've got a length and width in centimeters, but your thickness is in inches, you need to convert those inches to centimeters first. Then you can calculate your volume. Remember that the liter is the basic unit of volume in the metric system. The definition of a liter is the volume occupied by a cube that is 10 centimeters on each side. If you multiply 10 centimeters by 10 centimeters by 10 centimeters, you get 1,000 cubic centimeters. That is what 1 liter equals. So we know that 1 liter is equal to 1,000 cubic centimeters, which is what that statement says. We also know from our prefixes and writing those equalities that 1 liter is also equal to 1,000 milliliters. If both 1,000 cubic centimeters and 1,000 milliliters equal 1 liter, then we can also say 1,000 cubic centimeters is the same thing as 1,000 milliliters. You can simplify that down to say 1 cubic centimeter is the same thing as 1 milliliter. So when you're at the doctor's office or you're watching some kind of medical show and they say, we need 5 cc's of something something stat, the cc is a cubic centimeter. So it's the same thing as saying milliliters. Let's do a sample problem. An automobile engine displaces a volume of 498 centimeters cubed in each cylinder. What is the displacement of a cylinder in cubic inches? And then here is the unit equation. 1 centimeter is equal to 0.394 inches. We know that volume is equal to length times width times thickness. And the volume we're given in the problem is 498 cubic centimeters. The question, we have to take that 498 cubic centimeters and convert it to cubic inches. What we're given is the unit equation. 1 centimeter equals 0.394 inches. We can write unit factors from that. If this is kind of a question mark for you, the unit equation and the unit factors, you may need to revisit part 1. So I'll label these unit equation, unit factors. We're ready to set up our equation. 498 centimeters cubed. When something is cubed, that means it's something times something times something, right? So that's centimeters times centimeters times centimeters. So when we do this conversion, we have to use our conversion factor, or the unit factor, 3 times, because we have to cancel out centimeters 3 times. We've got centimeters in the numerator, and we need to have inches instead. We're going to choose this second unit factor, so we get rid of the centimeters and we're left with inches. And I'm going to write this in a few different colors just to demonstrate the point. So I've written it in multiple colors, and we're going to cancel out the centimeter each time. So we've got inches. Now write it up here. So we're building. We cancel another one, and now we're at inches squared. But we still got 1 more centimeters to cancel out. Now we're at inches cubed. So the multiplication you're doing is 498 times 0.394 times 0.394 times 0.394. That's what you're putting into your calculator. When you do that, your calculator will give you an answer of 30.4592, bunch of numbers. However, the information we're given in the problem, that's got 3 sig figs. We need to round our answer to 3 sig figs. So that means we're going to keep the 4 as our last retained digit. It's the last one we're going to keep. And we look at the 5 to see if we round up or stay the same. 5 is 5 or greater. So we're going to round that 4 up to a 5. Oops. 3 sig figs. So there's our final answer. Again, make sure that you multiply by your conversion factor 3 times. Because you've got to change that something cubed to something else cubed. Everything isn't going to be easy to measure with volume. Let's say that you have some kind of an irregularly shaped solid, or you have some kind of a gas given off, right? How do we measure the volumes of these things? For a solid or gas, we can use what's called volume displacement. We're going to take a liquid and put our solid in it, or our gas, and we're going to displace water. It's just like if you take a bath, like literally run the water in the bathtub and sit down in the bathtub. When you sit down, the water level rises. That's water displacement. The water's making room for your body, right? And the volume of the water, the apparent volume, after you sit down in it, that's the same as your volume, okay? So we're going to do the same thing with our solid. If I have a sample of green jade, and I start with 50 milliliters of water in a graduated cylinder, then I add my solid, and now I have a final volume of 60.5 milliliters. Then I can figure out the volume of my solid. And that volume is the final volume minus the initial. In this case, we have 60.5 milliliters minus 50 milliliters. So that's 10.5 milliliters. Now for solids, the units for volume of a solid is centimeters cubed. What we have is milliliters. But remember, 1 milliliter is the same thing as 1 cubic centimeter. So we can rewrite that as 10.5 cubic centimeters. For gases, it's a little bit different, but the idea is the same. This is your experimental setup. You've got a Bunsen burner, and you're heating up your reaction in a tube. You're forming a gas, and that gas will go through this tube and push down onto the water that is in this flask. So it exerts pressure. When that happens, it causes the water to go up this tube and into this beaker. The volume of water displaced into this beaker is equal to the volume of your gas. So you're displacing the water in the flask, putting that pressure down, causing the water to go up the tube and come out into the beaker. For these problems, you might see, the gas is pushed into some kind of a flask that has 100 milliliters of water and 60 milliliters of water are displaced. What we care about is the 60 milliliters displaced. The volume that is in that flask doesn't matter unless we're told an initial and a final volume for that flask. What we care about is how much water was displaced. For gases, we usually use liters. You might see milliliters as well, but typically you'll see liters. And we'll put the concept of volume together with the concept of density. So density is just a measure of its concentration of mass, right? We define it as the mass of the object divided by the volume. The mass you can measure using a scale. And the volume you can use, if it's a liquid, a graduated cylinder, or some other measuring apparatus for liquids. You can use volume displacement like we just talked about. For solids and gases. Once you have those two values, you can calculate density. Density is expressed in grams per milliliter for liquids, grams per cubic centimeter for solids, and grams per liter for gases. And down at the bottom, we've got 4 different substances: ice, water, lead, and osmium. The volume is the same, 1 cubic centimeter. However, the masses are different. So if you have a smaller mass, then you're going to have a smaller density if the volume is the same all the way across. So that's what that's demonstrating. You can have the same volume, but you can fit more mass inside of that volume, and that means that you have something that is more dense. This table has a list of common substances and their densities. You may need to reference this during your time doing homework, but I will never ask you to, remember the density of a substance. If you need it for a calculation, I will give it to you. We can also estimate density. We can just compare the densities of different objects and have a relative idea of how dense something is. A solid will float on top of a liquid with a higher density. So let's say that we have a graduated cylinder and we've got 3 different liquids: L1, water, and L2. Let's not even address the solids yet. We've got a liquid sitting on top of water, which is sitting on top of another liquid. if you've ever had salad dressing other than ranch, if you've had any kind of a vinaigrette, it will separate. So in the grocery store, when you buy it, or if you're making it yourself before you mix it, the oil and the vinegar do not mix. Vinegar is primarily water. It's like 6% acetic acid, a lot of water. Water is more dense than oil. So that oil will just kind of hang out on top, won't mix. You need to emulsify it. So you add something that will help the two mix together and stay together. And you can also do a lot of whisking or shaking, and that will help them to mix as well. Now back to the concept of density. When you have one liquid sitting on top of another, one is more dense than the other. The one that's on top is the least dense. The one on the bottom is the most dense. The same concept is going to work for these solids. The least dense solid will be the closest to the top. And it is sitting on top of the interface between the liquid 1, or L1, and water. So that means that in terms of density, the density of L1 is less than the density of S1. Sorry, I forgot the D there. Trying to keep all these letters straight. So the density of L1 is less than the density of S1, the solid one, which is less than the density of water, because that solid is sitting on top of the water, which means it is more dense. Now let's do that for S2. S2 is sitting on top of L2. So it sank all the way down through L1, through the water, and it's sitting on top of L2. If this is our density of S2, stop and think for a second. You can pause the video. Is water more dense or less dense than S2? Water is less dense than S2 because S2 sank down through it, okay? If it was just a cylinder of water, that solid would be sitting at the bottom of the water. It's more dense. L1 is also less dense. However, L2 is more dense. Let's do the third one just to make sure that we just drive the point home. This question, you're going to get a question like this on the exam. And it shouldn't trip you up. It's one of those questions that seems too easy because logic says, oh, well, it should be this, right? And then you second guess yourself. Don't do that. It is that simple. Now we've got the density of S3. It is sitting on the bottom of the graduated cylinder. That means it is the most dense. So L2 is less dense. Water is less dense. L1 is less dense. I didn't put all the solids in there, but everything is less dense than S3. We'll do another practice like this in class, just to make sure that you get it. Let's do some calculations with density. What is the density of a platinum nugget that has a mass of 224.50 grams and a volume of 10 centimeters cubed? Remember that mass over volume gives you density. Our mass is 224.50 grams. It has a total of 5 sig figs, because remember, you always have to think about sig figs. The volume is 10 centimeters cubed. It's a decimal number, so all of these zeros are significant. 3 sig figs. This means that our density needs 3 sig figs. That's the rules for dividing. We're dividing two numbers. We report the number with the fewest number of sig figs as our given information in the problem. So let's write it out. You can just move the decimal point because you're just dividing by 10. But that's not our final answer. We need 3 sig figs. We're going to keep everything up to the 4. We're going to look at the 5 and see whether or not we need to round up or stay the same. We need to round up. This is our final answer. 22.5 grams per centimeter cubed. That's it. That's calculating density. Now let's make it a little bit more difficult. We can use density as a unit factor, and I'll show you how. An automobile battery contains 1,275 milliliters of acid. If the density of battery acid is 1.84 grams per milliliter, how many grams of acid are in an automobile battery? Here, what we're given is 1,275 milliliters of acid and 1.84 grams per milliliter. And our question is the number of grams of acid in the battery. Well, what we have is a volume, 1,275 milliliters, and we have a density. We know density is equal to mass times volume. Well, the question is looking for the mass. So we can rearrange this equation and figure out what our mass is. Let's do that. Multiply by the volume on each side. That way, we've got density times our volume is equal to mass. Now we have both parts to figure out the mass. Our density is 1.84 grams per milliliter. And we're going to multiply that by 1,275 milliliters. When we look at density like this, it looks like a unit factor, right? We've got a unit per other unit. We can convert. We're canceling out the milliliters, and we're left with grams. When you do that calculation, your calculator will tell you something like this. But we have to think about sig figs. Let's go back to our volume. We've got 1,275 milliliters. That's 4 sig figs. Density, 3 sig figs. So our answer needs 3 sig figs. The 4 is going to be the third sig fig. So that's going to be rounded. We look at the 6 to see whether we round up or we stay the same. 6 is definitely 5 or greater. So we're going to round the 4 up to a 5. But we need a placeholder 0. Can't just write 235. The other way you could write this with 3 significant figures is using scientific notation. And you don't have to think about a placeholder 0. You just write it in scientific notation and you've got your 3 sig figs right there. Either way would be acceptable for this question. The next concept we're going to cover is temperature, and this is something that you have likely already seen. Temperature is a measure of the average kinetic energy of individual particles in motion. So if you think about the air around you, that's a gas. It's got oxygen and nitrogen and a bunch of other stuff, and all those particles are moving around. It's wintertime. Now it's North Carolina, so it ain't that much winter, right? But it is kind of chilly, okay? That means that the average kinetic energy of the molecules in the gas is going to be lower around this time of year. When we get to the summertime, like July, it's going to be a little bit higher. The temperature in February is lower than the temperature in July. Makes sense, right? There's 3 temperature scales we're going to talk about. Fahrenheit, which is represented with the degree sign and a capital F. Celsius, degree sign and a capital C. And Kelvin, which is simply a K. Kelvin is an absolute temperature scale. So it's no degrees, okay? We're just saying this is what the temperature is. And when we get to 0 Kelvin, then that means no kinetic energy. So you've got no moving particles. But when we get to 0 degrees Celsius or 0 degrees Fahrenheit, we can still go lower. We can have a negative, 5 degrees Fahrenheit or Celsius. Now here are the temperature scales and some comparisons. If we look at the temperature that water freezes at, Fahrenheit it's 32 degrees, Celsius it's 0, in Kelvin it's 273. Water boils at 212 Fahrenheit, 100 degrees Celsius, and 373 Kelvin. All three temperature scales are describing the same thing, it's just that their scales are different. Fahrenheit and Celsius are relative scales. Kelvin is not, it's absolute. Here are the equations that you need to convert from one to the other. So let's say that you had a temperature in Celsius and you want to calculate Fahrenheit. That's what this first one is, taking degrees Celsius to degrees Fahrenheit. The second equation is taking degrees Fahrenheit and going to degrees Celsius. If you want to convert from Celsius to Kelvin, you add 273. And likewise, if you want to go from Kelvin to Celsius, subtract 273. Note, you cannot go from Fahrenheit to Kelvin. There's no direct way to do that. You must, if you have a temperature in Fahrenheit that you need to get to Kelvin, go from degrees Fahrenheit to degrees Celsius, and then degrees Celsius to Kelvin. You cannot skip over the Celsius step. So let's do a sample problem like that. Body temperature is about 98.6. What is your body temperature in Kelvin? We first got to take those degrees Fahrenheit and convert to Celsius. So this is our equation. We'll fill in our body temperature. 98.6 minus 32. And then we have this ratio. You get 37 degrees C, okay? So that was the first step, going from Fahrenheit to Celsius. Now we need to go from Celsius to Kelvin, which is quite a bit easier. You get 310. But let's look at our sig figs. We've got 3 sig figs in our problem. So how do we represent that? Because as our number stands, it's only got 2 sig figs. We have 2 options. Plop a decimal point after the 0, and that gives you 3 sig figs. Or scientific notation. That will also give you 3 sig figs. That's the most complicated problem you'll have to do with temperature. Let's move to a related concept, heat. If temperature measures the average energy of particles in a system, heat will sum up all of the energies of all the particles in a system. It's the total energy. Oftentimes you'll see heat expressed as joules, that's the SI unit, or calories. And you can see their abbreviations, the J or the CAL. Now calories are probably like, calories, I think I know what that is. Calories you normally see on nutrition facts with a capital C. But it's actually not the same thing as the lowercase c. The capital C calories, and this is purely for your knowledge, is actually equal to a kilocalorie. Which is 1,000 calories. So just for your knowledge, all of these things are coming together. I hope you can see some of the relevance of the things we're learning here. It's not abstract. Let's compare heat and temperature. Now we said with our definitions, heat is the sum of all the energy of all the particles in a system. Temperature is the average energy of a particle in the system. If we've got 2 beakers that have water at the same temperature but different amounts, the one on the left has 500 milliliters, the one on the right has 1,000, the beaker on the right, the one with the 1,000 milliliters, has twice the amount of heat. And that's because even though they're at the same temperature, you've got 2 times the volume, right? That means that your system is 2 times as big. And if heat is the total energy, well, you've got more particles that have energy in beaker B. More particles at the same temperature means more heat. Now let's do a sample problem. This is another one of those problems that it seems too simple, so you second guess yourself. Don't. Pause the video, do the question, and then rejoin me. Which beaker has more heat? We've got a beaker with 250 milliliters of water at 90 degrees Celsius on the left, 500 milliliters of water at 45 degrees Celsius on the right. This system on the right is bigger, right? 2 times the volume. But the temperature is half. So these beakers actually have the same amount of heat. The system is bigger on the right, but the temperature is lower. And it's exactly half of the temperature of the beaker on the right. This is about as tricky as it gets. The other thing that I could do here is I could make one in degrees Celsius and one in Fahrenheit or Kelvin. Then you'd have to do a temperature conversion and then compare the 2 systems. Not trying to trick you, Trying to make sure you're paying attention. And I'm giving you the keys to the kingdom because you will see a problem like that on the exam. Watch for units. The final concept we'll go over for Chapter 2 is specific heat. Specific heat is just the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So if I had 1 gram of water, how much energy do I need to put into that water so that it goes from, say, room temperature to 1 more degree Celsius, right? So if your home is like 70-ish degrees Fahrenheit, then that's like 21-ish degrees Celsius. So we're going from 21 degrees Celsius to 22 degrees Celsius. That's what specific heat is. We represent specific heat with a capital C. And that's what you see here in the equation. To calculate specific heat, you've got heat in joules, that's the Q, divided by the product of the mass of your substance times the change in temperature, that's the delta T. The units for specific heat are joules per gram degree Celsius. Let's do a sample problem. This is probably about as difficult as it can get for your homework with specific heat. You're performing a reaction in a flask in a water bath. During the course of the reaction, you've got 1.50 times 10 to the 4th joules, not kilojoules, of heat moving from the flask to the water bath. The initial temperature of the water bath was 27 degrees Celsius. The mass of the water bath is 2,450 grams, and the specific heat of water is 4.186 joules per gram degree Celsius. Calculate the final temperature of the water bath. Kind of a lot to do, right? It seems like it. So our question is the final temp of the water. What we know, or what we're given, we've got an amount of energy in joules, and that's going to be very useful to us. We've got a mass of the water bath, and we've got a specific heat. We also know the temperature that the water started at. Remember our equation. We've got specific heat, which is the C, equal to the heat divided by the mass times the delta T. What we don't know in this equation is delta T. Delta T is the final temperature of the water, which we don't know, minus the initial temperature of the water. So our game plan here we're going to rearrange the equation to solve for delta T. Then we're going to plug and chug, which is just simply you put in your numbers, you get the number. Then we're going to calculate our actual final temperature. Because delta T tells us the change in temperature. Not what the final temperature is. To rearrange the equation, the first thing we're going to do is multiply both sides by m. That's our mass. We'll get rid of the mass on one side, and then we'll add mass to the other. So now we've got C times m is equal to Q over delta T. Now we're going to divide by delta T. Or excuse me, divide by Q. We're going to cancel those Q's out. Trying to do all the colors so that we keep track here. So 1 over T, that's not quite going to get it. So we need to do the inverse. So you get delta T is equal to Cm over Q, and you want the inverse of that. Inverse simply means, and I'll write it up here, if you've got something to the -1, on your calculator, there may be a 1 over x button. So that's all that means. And the way that you put this into your calculator, I'll write that in green so it stands out. You take your C, 4.186, times the mass, 2450, divided by Q, 1.50 times 10 to the 4th. Then you do that inverse button. And that will give you about 1.46. But this is our delta T. That's the temperature change, not the final temperature. For the final temperature, we have to add this amount to our initial temperature. So we have 27 degrees Celsius as our initial. We add 1.46 degrees Celsius. That's 28.46. But remember, with sig figs, we can't have that many. So it's 28.5 degrees Celsius. Kind of a lot. That's why we went through it here. And you can kind of go through it again step by step. We'll also do a practice problem in class to make sure that you get it. But this is as complicated as it gets for specific heat. That's why I wanted to show you this type of a problem. That way, everything else will be a lot easier. So if you're looking at this like, well, maybe I should just change my major. Don't, okay? I promise you, we'll make sure that you get it in class. When you watch it done, it kind of seems like a lot of math. But when you go through the process yourself and you understand how the steps are connected, you'll be good to go. Thanks for watching. Make sure that you tune into the live lecture for more practice problems and details regarding assignments and exams. So stay safe.